Greetings everybody, and today we're going to be taking a look at the integral from 0 to infinity of log of x over x squared plus 1 but the whole denominator squared. So I've actually already made a video on this, I think back in 2020, so quite a while ago, and yeah, that was one of my improvised integral videos. Tried making a bit of a series out of it back then, but only lasted for one video. But I might bring it back though, depends on if I have more integrals to try improvise. So if you guys have any integral suggestions you want me to try live for the camera, then drop it down in the comments below or send me an email, and yeah, I might do it if I feel like doing it and whatnot. And yeah, if it works out, then I'll post it, of course. So what are we taking a look at today? We're taking a look at this integral. We already know the answer to it. You can watch my video, the improvised integrals one on it, if you want to know the answer. Actually, it's just minus 0.4. So that's the answer, and it's not much of a calculation in this video. I guess it's more of a discussion on a specific complex analysis technique involving logarithms. I don't think it's mentioned so often in courses and whatnot. I think it's more of a integration trick kind of thing. So usually, well, what I did in my improvised integrals video was I constructed a little bit of a semicircular contour with an indentation, and for this we used the function f of z, and that's equal to log of z divided by z squared plus 1 but the whole thing squared, so basically the integrands. And this works out perfectly fine for this contour. However, on Wikipedia, which is where this example also pops up, what they did was they used a bit of a keyhole contour. I think they orient it in the negative direction. So this is our keyhole contour with the branch cuts from logarithm oriented this way. And if you use a keyhole contour for this integral, this function actually won't work, because your integral should be able to you should be able to recover it from these path integrals. However, if you use this function, the logarithm actually disappears. Now, this is a problem, of course, because if you can't recover your I, then if you try using the residue theorem, you're going to get two poles, by the way, at plus or minus I. Then there's no way to get your original integral back, which is a really big problem because that's what we're trying to solve. Now, if we have branch cuts and stuff like this, then usually it's fine just to replace the integrand with its complex version. For example, if we have powers, fractional powers or something, let's say x to the p, where p is some fractional power, then of course you're going to get a branch cut. But if you integrate above and below, you're actually going to pick up a bit of a factor. I think it's something like e to the 2 pi I times p usually, that you pick up on the bottom integral or the top integral, depends on how you define the branch cuts. But yeah, there's this factor that you can work with and turn stuff into sines and cosines and whatnot. However, with the logarithm, you don't get this e to the 2 pi I factor out the front. The reason is, if you take a look at the complex logarithm, log of z is equal to log of the absolute value of z, and then you have plus I times the arguments of z. Now, this is the definition. It's really quite unfortunate in this case, because the logarithm, log of absolute value of z, this is essentially what's going to recover our original integral. However, if you integrate above and below the branch cuts, log of absolute value doesn't know if you're above or below the branch cuts. And these branch cuts, these path integrals above and below the branch cuts, they're going in opposite directions, which means if you try to integrate, say, over psi 1, so let's say this is psi 1 and this is psi 2, if you integrate over psi 1 of your log of absolute value of z, and then you have plus the integral over psi 2 of log of absolute value of z, then what actually happens is that, in the limits, psi 1 and psi 2 are negatives. So this is negative psi 1, or just put a negative here, and the logs are going to cancel. Of course, you're going to get other stuff as well in the denominator, and this argz stuff. But the main thing, which is the logarithm, which is what we use to recover our integral, those are going to cancel, and you're basically left with nothing. So how do we kind of remedy this? Well, the trick is, I think it's called squaring the logarithm or something, but in general, if you have log to some kth power up here, then your function, if you decide to use a keyhole contour, you should add 1 to the power. So in this case, we're just dealing with log of x. So what our function should be, it should be log squared. So this is just a little bit of a trick that you use. Now, why would this trick work out over here? It's because if you take a look at log of z, the whole thing squared. Now, what happens if you expand this out in terms of real and imaginary parts? Well, you're going to get log of absolute value of z plus I times arg of z, and then this is the whole thing squared. And this might seem like something funny to do, but remember, if you expand this out, you're going to get log squared absolute value of z plus something like 2i arg of z, and then plus, some constant junk, which involves I times arg z. This is a really good thing, because if you integrate along one way and then the other way, well, this log squared of absolute value of z, well, those are going to cancel. By the way, I forgot the logarithm here, so there should be an extra log absolute value of z here, and so on. However, this part over here, this won't cancel, because above and below the branch cuts, these argument values will be different. So you're basically going to get some factor of log of z out the very end, which is exactly what we want to recover our original integral I. So this is why the trick works. It's because the log squares will cancel, and the linear factors, well, above and below the branch cuts, they won't be the same because the arguments are going to be different. So it's a pretty cool trick, in my opinion. Not one that you see a lot. It's only specific to integrals where you have logarithms and so on. But yeah, let's try to use this, and hopefully, if none of that made sense or anything, or if it was too confusing, then hopefully you'll see it in action when we perform some integrals. So we're going to be using, as I said before, the keyhole integral. We're going to get two poles, plus or minus I. These are double poles because you can check the multiplicities are an order of 2. Now, on Wikipedia, they have the branch cuts oriented in the negative direction. I don't know why they did that, why the person who wrote that did that. It's a bit weird. You could have them in the positive direction as well. They actually work out the same way. You're going to be basically off by the same arguments, if you like. But we'll just take the positive direction, and you can do the same thing for the negative direction if you really want to. And we'll make a little bit of a integral, or I guess a circle around this rather. And we'll call the whole entire contour C. It looks like a C as well. I'll call the outer path gamma, and then we'll have side 1, side 2 in here, and the little path inside little gamma. Okay, so the contour integral over C is equal to the integral over sine 1 plus the integral over sine 2 plus the integral over gamma plus the integral over big gamma. And in the limits, as these, the big circle grows and the little circle shrinks, these are going to vanish. I won't show that in this video. I've done that plenty of times. So if you want a full explanation, then check out some of my other videos where we have branch cuts and branch points. Essentially, this denominator here is going to outgrow the logarithm squared. So that's why the integral over big gamma vanishes, and the reason why the integral over little gamma vanishes is because we're integrating around the branch points, and whenever you integrate around the branch points and take the limit as that little circle tends to 0, then it's just going to vanish. So this leaves us with the contour integral over C being the sum of the integrals over sine 1 and sine 2. Now the integral over C, we know how to evaluate this. This is just the residue theorem. It's 2 pi I. Now we're going to get two residues. So we're going to have the residue at Z equals plus or minus I of f of Z. So this shouldn't be too tricky to do. It might be a bit boring to do though, because we have to differentiate stuff and plug stuff in because we have a double pole. Let's actually do an example of that. So I'm going to take a look at the residue at Z equals I of, let's take f of Z, but that's going to be the limit. Actually, no, this is a double pole, remember, because if you factor this, you get something like a Z minus I squared. So we want to use the definition for or the formula for residues at high order poles, that goes something like 1 divided by the order minus 1 factorial, which in this case is just 1 over 1 equals 1. Then we take the limits as z approaches the pole, which is I. Then we take the first derivative, so in general it's n minus 1, so n in this case is 2, so 2 minus 1 is 1, so first derivative of z minus the pole raised to the order of the pole, which in this case is 2, times your function, which in this case is log squared of z, divided by, I'm going to write this as a z plus I, but the whole thing squared, and then z minus I, but the whole thing squared. So this is how we factor this denominator. Now z minus I squared and z minus I squared, those are going to cancel, and what we can do is we can, let's rewrite this a little bit over here. This is derivative, actually we have the limits as well, so we have the limits, z approaches I, derivative of, we have the logarithm of z divided by z plus I, but the whole thing over here, we're going to square that. So evaluating the derivative, well, we can use chain rule, for example, the chain rule, as some people call it. So z approaches I of, we have, well, power rule first, so 2 log of z over z plus I. And then we multiply by the derivative of this inside. That's a quotient rule. So we have vu dash, so this is z plus I, times 1 over z minus u, and then we have a v dash, so log of z, v dash is 1, and divided by z plus I, but the whole thing squared. Okay, and we just take the limits now, so nothing blows up if we plug in I, so let's just sub in I, so we have, I guess, 2 log of I divided by, this is going to give us 2I, then we have z plus I, which is 2I times 1 over I, and then we have minus log of I divided by, this is 2I, but the whole thing squared. Okay, so these 2's are going to cancel, anything else that cancels, these i's are going to cancel, and this 2I but squared is just minus 4. So what do we have? We have, let's bring, so you have I into negative, so negative I in the denominator is the same as I in the numerator. We have the logarithm of I, so this is I, and we also have the division by 4, so I over 4 log of I, and then we have the times, this is 2 minus, and then log of I. What exactly is log of I? Well, what is the branch we're choosing? Well, it's pretty clear. In this case, it's arg of z on the interval 0 to 2 pi. So on the interval 0 to 2 pi I, you can write as e to the I pi over 2. And well, the log and the e will cancel, leaving us with I pi over 2. So this is I pi over 2, and we can do the same thing over here. This is I times pi over 2, and let's simplify this. I and I, that's just a negative 1, and we can expand everything inside. So this is going to become, in the end, we have minus 2 and 2 here are going to cancel, leaving us with a pi over 4. And then we also have, if you expand into here, I believe you get, well, negative, that's a positive. 4 times 2 times 2 is 16, so we have something like I pi squared over 16. That should be correct. So the residue at z equals I is this guy over here, and greetings once again, this is me from the future after the original video got released, which was, I think, what you guys were watching for the past 10 minutes. And yeah, after that transition or cut there, I realized I made a few major mistakes, and that's no good. Yeah, I was just improvising most of the time. I didn't have notes or anything, so I didn't really pick up on those mistakes. Anyways, we didn't calculate the residue at z equals minus I in the original video, and that turns out to be quite important. I just assumed that we would just get an extra negative here instead of a plus, but no, I copied that off of Wikipedia, and Wikipedia was using the branch minus pi to pi. Here we're actually using 0 to 2 pi, so it's going to be a bit different. So what is that going to be? Well, that's a double pole once again, so we have 1 over 2 minus 1 factorial, which is just 1. Then we have the limit as z approaches the pole of the first derivative of z minus the pole, which is z plus I. Then we raise it to the order, which is 2, times our function, so log squared of z divided by z. And then we have plus I, but the whole thing squared, then z minus I, but the whole thing squared, and these are going to cancel. And we now have to evaluate the derivative, so we have the limits, z approaches minus I, derivative of, we have the logarithm of z over z minus I, but then this is squared. So now we can just use a bit of chain rule once again. So this is the limit as z approaches minus I of 2 logarithm of z divided by z minus I. So that's the outside derivative. Now we multiply by the inside derivative. And that's going to be, well, this is quotient rule, so we're going to take v, then u dash, which is 1 over z. Then we have minus uv dash, so that's just going to be log of z. And we divide by z minus I, but the whole thing squared. So now it's safe to plug in minus I into everything, nothing's going to blow up. So we're going to get 2, then log of minus I, divided by, this is going to be minus 2i down here. Then what are we going to get over here? Well, this is going to be minus 2i divided by I, so multiplied by 1 over I guess, or minus I actually. We're plugging in, minus I. Then we have a minus the logarithm of minus I, all divided by, this is going to be minus 2i, but the whole thing squared. Okay, so now we can cancel some things. These 2's are gone. Notice we have a minus I, but if you have minus I on the denominator, that's the same as having I in the numerator. Then we have the logarithm of minus I. Now here we have to be careful because minus I on this branch is represented by e to the I 3 pi over 2. So when you have a log of e to the I 3 pi over 2, that is going to reduce down to I times 3 pi over 2. So not minus pi on 2, but 3 pi over 2. Then we have a minus, so these negatives cancel, these i's cancel, leaving us with 2. Minus, same deal over here, that's going to evaluate to I. Then we have 3 pi over 2. Then divide by minus 2i, but squared, that's going to be 4. Okay, so notice these, sorry, not 4, minus 4, because I squared is negative. So we have I and I, that's negative 1, cancels with this negative down here, and this leaves us with, well, let's distribute 3 pi over 2 into everywhere, and we're going to get, well, these 2's are going to cancel, leaving us with 3 pi over 4. Then we have minus I, then we have 3 and 3, that's going to be 9, pi and pi, that's going to be pi squared, 2 times 4 times 2, that's going to be 16. So that's going to be the residue at z equals minus I. So overall, this is, 3 pi over 4 minus I 9 pi squared over 16. So now what happens if we do the sum over here? So if we add these two residues together, then we're going to get, well, the real part that's going to evaluate to pi over 2. Then if you add the imaginary parts, that's going to be minus, so 1 minus 9, that's going to be minus 8 pi squared over 16, or just pi squared, or I times pi squared over 2. So that is going to be the sum of residues. So this over here, let's get rid of that. That's just going to evaluate to pi over 2 minus I pi squared over 2. And if you want, you can cancel the 2's here as well, and that's going to leave us with, and we can distribute pi times I into everything, so that's going to be I times pi squared. Then we have I times I is negative, so that's going to be positive pi cubed, I think. Yes, that should be right. Alright, so that's all the residues out of the way. Now the final thing to do is to compute the integrals over psi1 and psi2. So how do we go about evaluating the integral over psi1 of our function f of z? Well, our contour is traversed in the positive direction to anti-clockwise, so psi1 that's going to be going to the right. So if we write this out as a parameterization, we're going to from 0 up to infinity. Now notice we're approaching everything from above. Now what happens to log as we approach from above? Well, it's going to become log of the absolute value of z, and then we add I times the argument. So I think we discussed this before, so arg of z as we approach from above, but that's just going to be 0. So this is technically log of absolute value of z plus I times 0, and then this whole thing is being squared, and we divide by, now if we approach from above, well, this is just going to turn into z squared plus 1, but the whole thing's squared, so nothing really changes there. So notice on the interval 0 to infinity, absolute value, that's always positive, so we could just ignore it. And yeah, this leaves us with the integral from 0 to infinity of log squared of, let's choose a new variable, let's say t, and then we divide by t squared plus 1, but the whole thing squared dt. Okay, that's psi1. Now how about a psi2? So the integral over psi2, what is that? Well, psi2, we're going from infinity back to 0, so infinity to 0, of, we have log squared of z over here. But if we approach from below, then our log of z is going to turn into log of absolute value of z. Then we have plus I times the arg of z as we approach from below. But arg of z as we approach from below is going to be 2 pi. So this is plus 2 pi I. So this is the logarithm, but also we have to square the whole thing. So this is squared divided by, and as before, just like before, approaching from below, the denominator stays the same. So this is z squared plus 1, and the whole thing squared dz. And yeah, we could write this out a little bit. You could change the variables if you want. Let's flip the bounds. So this is negative integral from 0 to infinity of, let's expand out everything in here. So this is going to be log squared of t. Then we have plus, we have 4 pi I times log of t, because this is the binomial thingo right here. And then if we square 2 pi I, that's going to be 4 times pi squared, and then this I, that's going to become negative. So that's going to be minus 4 pi squared divided by, and yeah, t squared plus 1, and the whole thing squared dt. Okay. Cool. Another thing I'll do, I'll distribute this negative into the numerator, so negative, then this turns into negative, then this turns into positive. Alright, so I think this was another mistake I made in the original video. Someone pointed out that I got the signs mixed up or something. Hopefully it's correct now. It should be correct. So let's add these two integrals together because we're adding psi1 and psi2 here. So integral over psi1 plus the integral over psi2. What is that in the very end? Well, notice if you add these two integrals together, interval of integration is the same, so you can just add the integrands. Now you'll have a log squared over here, which will cancel with the minus log squared. This is exactly what we wanted. And notice, because the arguments are different above and below, the term with just the logarithm to the first power won't cancel, because the arguments are different. So over here, we're left with the integral from 0 to infinity of minus 4 pi I log of t, and then we have an extra plus 4 pi squared over here. So plus 4 pi squared, and this is divided by t squared plus 1, but the whole thing squared dt. Okay, and in the end, what do we have? Let's split up the integral a little bit. So this is minus 4 pi I. Then we have the integral from 0 to infinity of log t over t squared plus 1, but that's exactly I. So 4 pi I, capital I. Then we also have plus 4 pi squared of the integral from 0 to infinity of 1 over t squared plus 1, and the whole thing squared dt. So this is the result if we add psi1 and psi2 together, and we know this thing over here must be equal to this 2 pi I times the sum of the residues, which is what we have up here. So now we'll compare our results pretty much. So what can we conclude from this? Well, notice we have an imaginary part and a real part. Imaginary part and real part. So the imaginary parts must be equal. So in particular, minus 4 pi I, capital I, must be equal to I times pi squared. Okay, but the i's cancel over here. Pi and this squared will cancel, and this leaves us with I being equal to minus pi over 4, exactly what we wanted. And yeah, as an extra, we also get for free the integral of 1 over t squared plus 1. All you have to do is divide this guy by 4 pi squared, and that's going to give you something like pi on 4. Yeah, so this integral evaluates to pi on 4. So we kind of get 2 integrals for free by doing this. So that's pretty much the idea for this video. That's how you evaluate it using the keyhole contour. Pretty nice trick though. This generalizes to if you have log of even higher powers. This is something you could do. And yeah, that's pretty much all for this video. I hope you guys enjoyed it and found it useful. And up until the next one, have a wonderful day. And I'll see everyone in the next one. Bye bye.